Y'all, it's super late and I can hear my dog down the hall snoring, and it's about the cutest thing I've ever heard. So I'm dying right now. I just want to go snuggle with her so bad. But here we are. Instead of snuggling with sweet little Winnie, we're going to talk about composite functions and inverses where we're dealing with cosine. Okay? So it's going to work essentially the same way that things worked with sine. We know that a function and its inverse, they undo each other. Okay? Ideally. All right? So we have a situation here where it says, given that g of x equals cosine x and g inverse x equals inverse cosine x, it follows that. Now, it might be easier if you think of this right here as theta and theta and theta and theta, if that's helpful. If not, it's no big deal. I was copying and somebody let me borrow notes that they use, so I was kind of copying and pasting and different notation. All right, so anyway, if we take g inverse of g of x or g of theta, then that means we're taking inverse cosine of x or cosine theta, and what we're going to end up with is just the input value for cosine, because cosine and inverse cosine, they just undo each other. Now, this is true as long as x or theta is in the correct domain. And we know that we've stated that the domain of cosine, the very restricted domain of cosine, but we've set the domain of cosine to be 0 to pi. Okay, so inverse cosine will undo cosine as long as the input of cosine is in that domain. Now, on the flip side, g of g inverse of x equals cosine of inverse cosine of x, and that's going to equal x, the input, as long as that input, that ratio, the input for inverse cosine is in the domain of inverse cosine. So please remember, let me do this in regular ink. The domain of cosine is 0 to pi. The domain of inverse cosine is -1 to 1. So keep that in mind, just like we had to with inverse sine and composite functions, we have to do the same thing here. So you always, always, always want to make sure that you're meeting the domain requirement of the innermost function, okay? So for example 8, it says find the exact value of each composite function. So we have inverse cosine of 2 pi over 3. So since the input function is regular cosine, we're looking at an angle. So we have to make sure that we're meeting the domain for regular cosine, which again, this is restricted cosine. So is 2 pi over 3 in 0 to pi? And the answer is absolutely yes. You can think of 2 pi over 3 as like 2/3 pi, and 2/3 is definitely somewhere between 0 and 1. Okay, so we're good. So we would say, yep. So that tells me that these two can successfully just undo each other because we've met the domain requirement for the input function. So these will just undo each other. And that just leaves me with my input of the innermost function. So that would be, this equals 2 pi over 3. So as long as you meet that domain requirement, it's really, really quite simple. You just have to make sure you meet the domain requirement. And something like part B, yikes. Okay, so let's look at part B. We have inverse cosine of -pi over 3. So since the input function is regular cosine, the innermost input is an angle, okay? So we have to make sure we meet the domain for just regular cosine, which tells me that whatever angle I'm chewing has to be chewing. Am I hungry? I don't know, maybe. Whatever angle I'm choosing must be in the restricted domain that we set for cosine, okay? So the question here is -pi over 5 in 0 to pi? And the answer is nope, sure isn't. Okay, so we kind of have a problem. So let's think about this. It always helps to draw a picture. So we know that when we're dealing with inverse cosine, we have to be between 0 and pi. So this region right here. Well, unfortunately, if we look at this angle, -pi over 5, we're not in that restricted domain. We're like down here. Well, let me draw that a little bit better. Okay, so we're down here. Okay, so this right here is negative pi over 5. Well, that's outside the domain restriction that we've set for cosine. But as long as you're talking about the input, like the innermost input being an angle, we can play around with this idea of reference angles. So remember, reference angles are always the acute positive angle that takes you from the terminal side of whatever your original angle is to the x-axis. So let's think about what that would be. Let's do that in blue. So if I look at this angle, let me do it actually in blue. If I look at this angle right here, let's call that alpha. Well, that would just be positive pi over 5, which is in our domain restriction. So positive pi over 5, I need to go to bed. Positive pi over 5 is like right here. Okay, that is in our domain for cosine. So we can rewrite this because we know that a function, so like if we have cosine, so I can say that cosine of theta, the original function or the original angle, is equal to plus or minus cosine of alpha. Okay, so you just have to think about what quadrant the original angle is in and what cosine would be in that particular quadrant. So the original angle, negative pi over 5, is in quadrant 4. Well, in quadrant 4, cosine is positive. So that tells me that now I'm looking at this quadrant 1, okay? And that's part of my domain for cosine now, okay? So I can rewrite this. I can say, okay, we have inverse cosine of positive pi over 5, okay? And now because I'm in the correct domain, these two critters, they just undo each other. So that tells me this is equal to pi over 5. Now, you could also have taken into account that cosine is an even function. And so if you like the idea of cosine being an even function, you could have played around with that instead. But either way, you're going to get just pi over 5. Okay? So remember, once you get in the correct domain, as long as you're dealing with the angle we have a little more freedom. We can play around with reference angles. And as long as you can find an equivalent angle in the correct domain, then you're good to go. And the inverse cosine function and the cosine function, they'll just undo each other. All right, let's look at cosine of inverse cosine of 0.6. So this time the input, okay. This time the input is inverse cosine. Okay, well, let me write, I don't know why I wrote it like that. Oh, don't do this to me. There we go, I got it. All right. Since the input is inverse cosine, we're going to have to look at something different. Now, the domain of inverse cosine is negative 1 to 1. So is 0.6 in negative 1 to 1? And the answer to that is yes, absolutely. We're good. Okay. So since we're in the correct domain, and you're always looking at the domain of your input function, since we're in the correct domain, these two things will just undo each other. So we can say that this just equals 0.6. Okay? And then that takes us to part D. Part D is going to be a little weird. So part D, we have cosine of inverse cosine of 1.8. So the input here, the input function is cosine inverse, and the domain of, well, inverse cosine, the domain is negative 1 to 1. So is 1.8 in this interval of negative 1 to 1? And the answer is no, it's not. And because we're dealing with inverse cosine, the input is a ratio. So the input for cosine, inverse cosine is a ratio. And because it's not an angle, we are just really limited. This is outside of the domain. We can't do it. So we would just say this is not defined. So just be really careful when the innermost input value is an angle. We've got a little wiggle room. We can play around. When the innermost input value is a ratio, we can't really do much, okay? So in this case, 1.8 is outside of the domain of inverse cosine. We can't do anything. We just say this is not defined, okay? And I think that might be it for, yeah, so that's it for cosine inverse or inverse cosine. Let's look at the next one is going to be inverse tangent.